So when these two ligands in opposite z direction are moving, so let's write it down actually. So moving the two opposite ligands, let's say one from z and one from minus z side, the repulsion, we can say the repulsion between ligands and m plus electrons in d orbitals that have z character. That means dz square, dxz, dyz. Okay, energies are lowered. So what do I mean? So I mean that when you go from EG, we have seen that you go into, what was the two? For EG it is A1G and dz square and dx square minus y square. So that means dz square will be lower in energy as compared to dx square minus y square. And if you go from T to G, dxz, zx and dyz will be lower in energy as compared to dxy. This is the result of the lower repulsion along z-axis now. So when the repulsion is lowered along z-axis, the orbital energy along z-axis would also be reduced. So why these orbitals would reduce in energy? Because they have substantial z character in their orbitals. So whereas these ones have x and y characters, so these are along transverse axis or transverse plane, and these are along z-axis, right? So these orbitals would experience lower energy, these orbitals would experience higher energy. So let us see explicitly how the molecular orbital diagram changes in these two cases. So let's start from isolated atom, isolated ion with R3 symmetry, spherical symmetry. So from here we actually go to octahedral case, which can be written as like this. So this is my octahedral case, and this is T2G set, and this is EG set. Now this EG set further breaks, and I get this. Now this will be one orbital. This will be my dx square minus y square. And if I want to write the symmetry of this, this will be B1G, and this is dz square. The symmetry of this will be A1G, right? And these two orbitals, one will go up and two will go down. This will be dxy, this will be dzx and dyz. The symmetry here is now EG, symmetry here is B2G. Now this was OH and this one is now D4H point group. Okay, so and what is this case? This case is tetragonal elongation. Elongations because now the two Z ligands are actually taken apart, and hence that lowers the repulsion between orbitals of containing Z character and the ligand orbitals. So due to that decreased repulsion, the Z orbitals are actually decreased in energy. So reverse will happen if there is a tetragonal compression. So now if you're trying to compress the two or ligands along z-axis or along the opposite axis, the reverse will happen. So let us try to see how the MO diagram of that would look like. So in that case, you will again start with R3 and you will go to T2G and EG under octahedral, and now the reverse will happen. So you will have dz square and dx square minus y square, and the corresponding symmetries will come here, and you will have 2 here. Dxy will be lower, dyz and dzx. So this will be d4h only, but this is the case of tetragonal compression. So it is also, we should also be able to see that if there is a tetragonal compression and there is a stabilization of xy orbitals, then there is a corresponding destabilization of z orbitals. That means if on one side, that is z versus a transverse side, if on one side there is a compression of bonds, then the other side there will be a compensatory elongation of bond to match the energy, right? So that is, if there is a compression along z axis, there is elongation along xy axis. If there is compression along xy axis, there is elongation along z axis. So that is to stabilize or to balance the loss of energy and gain of energy. Okay. All right. So now that we have understood the Jahn-Teller distortion and the symmetry aspects of it, so let us also try to understand the bonding in using MO theory again. So the bonding is a molecular orbital theory for sigma bonding picture in OH complexes. Okay, so this is our next topic. So molecular orbital picture of bonding in OH complexes. So this we already know. I'm just, because we are on octahedral complexes, so I think it's better to describe this sigma bonding picture so that it is fresh in memory. Okay, so let's see. So what are the steps we have to take? So if you remember, we have to create SALCs using the sigma bonds like this. All right, so 6 vectors are chosen for creating SALCs of B atomic orbitals. Okay, so these will be called as, so you can say that the bases are sigma x, sigma minus x, sigma y, sigma minus y, sigma z, sigma minus z, right? So this, if you take all of this and create a reducible representation under OH symmetry, so you will have tau sigma, which will be E 8C3 6C2 6C4, and we have 3 C2s I, then we have 6 S4s, 8 S6, 3 sigma H, 6 sigma D. So do we have 48 now? 1 9 12. Yeah, so this is 48 all. So now if you consider this 6 basis vector and vectors, and which vector moves, which does not move, and use that principle to see what will be the trace under this reducible representation. So E will have 6, because this will be a 6 by 6 matrix. C3, everything will move, so 0. C2, everything will move to 0. C4, 2 of them will not move, opposite vectors will not move, so 2. C2, this is the C2, which is where again two of them opposite ones will not move. In I, everything will move. S4, everything will move. Everything will move. Sigma H, 4 vectors will not move, which are in plane. So 4, sigma D, 2 vectors will not move, right? Okay, so now upon reduction, using reduction formulas, sigma, this is sigma, tau sigma will give rise to A1G plus EG plus T1U. This comes from reduction formula. We can say using reduction formula. Okay. So that means 1, 2, 3, 4, 5, 6. So 6 dimensional representations or 6 dimensional IR representations are coming. So this would mean that there would be 6 SLCs with different symmetries, right? So there will be 6 SLCs with different symmetries, which can form bonding, anti-bonding, combinations with like atomic orbitals of M, that is the central metal atom. So what are the central metal atom symmetries under OH? So we can write down symmetry of M plus in OH. We can say that S transforms as A1G. So we have a matching over here. Then PX, PY, PZ, they transform as T1U. So we have another matching over here. So this set of SLCs can match with PX, PY, PZ. And then DXY, DYZ, DZX will match with T2G. There is no corresponding T2G, so these will remain non-bonding. Then DZ square and dx square minus y square will transform as EG. So this will also form bonding and anti-bonding. All right. So let's go to next over here. So now using PO, using projection operator will be a difficult approach here, because we are dealing with triply degenerate representation. Already in case of doubly degenerate, we have seen that how difficult it is, right, to find out the other SLC, like the second or third SLCs is not really trivial. So what we do is we will try to look for an easy approach. I'm just writing it down as easy approach. So what we do here is look for combinations of basis orbitals that have pattern matching the atomic orbitals of same symmetry. See, SALCs have to be combined with atomic orbitals. Now, if we find out the SALCs, pattern of SALCs combination that will match the symmetry of atomic orbitals, we can actually build up those SALCs, right? The same symmetry on the central atom. We will see how to do it. That's why I wanted to take this up, because this is a little different approach than regular projection operator approach. So for example, if we want to find phi A1G we earlier what we used to do is we used to take a projection onto any of the basis orbitals using A1G symmetry and find out, right? But now what we want to do is we want to match the symmetry of A1G with the A1G symmetry atomic orbital of central metal atom. So what is the central metal which orbital which has A1G symmetry? That has S symmetry, right? S orbital. S orbital is A1G. That means, so now the 6 SALCs should have same combination or same phase as S orbital. So we can say that this is, I'm directly writing after normalization. So 1 over root 6 I'm writing. So if I combine sigma x plus sigma minus x plus sigma y, so all of them have same phase, plus sigma minus y. Yes, y, x minus x are the directions, but the phase of the orbitals are all same. Plus sigma z plus sigma minus z. So this will have A1G symmetry, right? Because all the possible signs are positive in nature. So I can pictorially also represent it something like this. So if I have central metal atom as S orbital, which will be positively phased, and so my SALC phi A1G can be written as like this, can be drawn as like this. So I have positive, 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 positive. So all positives will match to give you the molecular orbital from this. So S of metal atom will combine with phi A1G of SALC of this B atom, right? So this can be labeled as phi A1G, right? So this is a very simple approach. So directly we have understood that what will be the combination of different orbitals based on the central metal atom orbital of same symmetry. So now let us move further with the next set orbitals. So now the EG, there are two EG ASLCs. Two EG SALCs can be obtained by matching symmetry with two EG orbitals of M. M is a central metal. So let us see the first one. First one here is dz square. This is positive, positive, and negative over here. And what will be the combination of different atomic orbitals here, which will give rise to an SALCs? So Z and Z side, we will keep them as positive to match positive, positive. And since X and Y, the whole belt is negative, so I will put negative phase here. Right, so this is my X, Y, minus X, minus Y. This is Z, minus Z. So my phi EG1 can be written as, again this will be, so I can have 2 sigma Z plus 2 sigma minus Z. So these two are positive. So remember that this is 2z square minus x square minus y square. So for 2z square, there will be 2 sigma z's and 2 sigma minus z, and the rest will be minus sigma x minus sigma minus x minus sigma y minus sigma minus y. And the corresponding normalization coefficient will be 1 over 2 root 3, right? So I hope this is clear. So because there is positive lobes along Z and minus Z, so we are taking sigma z as positive and sigma minus z as positive, because there is a negative belt around x and y transverse plane. So we are taking all sigmas along x and y as negative. And the factor of 2 comes because there is actually 2z square minus x square minus y square. So z square is 2. So that's why we are taking 2. And coefficient of z square is 2. So that means there is more wave function along z axis as compared to transverse plane. So that's why we are taking, to match this, we are taking this. Okay. So now the second EG is dx square minus y square. So we don't have to consider z axis here. So we have plus plus minus minus. So the SALCs will also be like this. So you have plus x minus x plus minus minus, right? So this is y minus y. So I can say phi EG second will be sigma x plus sigma minus x minus sigma y minus sigma minus y, and this will be 1 by 2, right? So you should be able to test out whether these are orthogonal or not by multiplying the coefficients of it and taking summation over it. So these all should be normalized and orthogonal. Okay, that condition we cannot skip. All right. So now for T1U, because the third symmetry was T1U, so 3 T1U symmetry SALCs can be obtained by matching with corresponding atomic orbitals of M. So now how do I do that? So T1U had atomic orbitals as px, py, pz. So if I'm trying to compare px, py, pz, so px is like this, right? This is my x, y, z, positive, negative, right? So what kind of atomic orbital combinations would happen to make SLCs? So now I will have a positive here and a negative here, right? This is my x, y, z. So my phi T1U 1 will be equal to sigma x minus sigma minus x. So positive on sigma x side, negative on sigma minus x side, and this will be 1 over root 2 for normalization. Similarly, phi T1U second will be 1 over root 2 sigma y minus sigma minus y, and the third will be phi 3 T1U 1 over root 2 sigma z minus sigma minus z, right? So now we have all 6 SALCs. So let us list them down. So phi 1, we have sigma x plus sigma minus x plus sigma y plus sigma minus y plus sigma z plus sigma minus z, and this is 1 over root 6. Phi 2 was 1 over 2 root 3. This is 2 sigma z plus 2 sigma minus z minus sigma x minus sigma minus x minus sigma y minus sigma minus y. And the third one was 1 over 2 sigma x plus sigma, these are two positives, minus x minus sigma y minus sigma minus y, and 3 are written here. So we have got 6 of them, 3 with T1U symmetry, 2 with EG symmetry, 1 with A1G symmetry, right? Okay. So now let us draw the MO diagram for this. Again, so MO diagram would be an approximate MO diagram. Actual energies would really depend on the extent of overlap between a particular metal ligand and what is the type of ligand, whether it's a high field ligand, strong field ligand, all those things would matter. But I'm just trying to give you an approximate MO diagram here. So we will have 5. Let's start with metal and B atomic orbitals, SALCs. So you have 6 SALCs here, and this is n-1 d orbitals, which will have EG set and T2G set. Okay. Then you have S orbital, NS, let's say, which will have A1G symmetry. Then you have 3p orbitals, NP, which will have T1U symmetry, right? So the orbitals are written with lowercase, whereas symmetry is written with uppercase. So I have mixed both of these. But if we are describing orbitals, then you will write lowercase letters with E and T. If you are describing the symmetry of that, then you will write with uppercase E and T, like I've written uppercase here. Okay. So either way is fine, but name of the orbitals go with lowercase, name of the symmetry Mulliken symbol go with uppercase. All right. So now if you have noticed that the symmetries here were A1G, EG, and T1U. So T2G really does not match, so that T2G will remain as non-bonding, right? So this I will write as lowercase. So T2G orbitals would not form bonding and they will just remain like this. Okay. Let me draw this picture. Okay. All right. Now EG, there are 2 EGs here. So EG will match with EG and you will get 2 bondings and 2 non-bonding or 2 anti-bondings. I will write EG here and EG star over here. Also this S will combine with one of this. So you will get A1G and the second will go over A1G. So again, these energies are not precise and even the relative energies of this will depend on the direction of the ligand approach, the repulsion, the extent of overlap. All those will define whether EG will be more stable or A1G will be more stable and so on and so forth. Okay. And this will be T1U. So T1U will come somewhere over here. But again, this might flip. So you will have 3 T1U, T1U, and you will have so star describes anti-bonding. This is bonding orbital and this will be non-bonding orbital, right? So this is an approximate, I will say approximate MO diagram for OH symmetry molecule, right? Let's say MB6. Okay. Now different books might have different diagrams where the symmetry of these 3 orbitals and these 3 orbitals might get flipped, because again I'm saying that this is, we can only get an approximate picture from group theory, and actual picture you will have to set up the secular equations and calculate the energy, but it does give you approximate explanation of what is going on based on symmetry. So that finishes our discussion on bonding, including now the crystal field theory. So in the next class which is the last week. The application which we'll be discussing is the spectroscopy. So we'll be looking at different types of spectroscopy there. So please, if you have not gone through any course of spectroscopy, so please go back and read a little about spectroscopy, so that it is easier when we are discussing that. All right. That is all for today. Thank you.